Hi, I'm Mr. Kangas, and today we're going to take a look at Chapter 9, Section 6, Similar Figures. Similar figures are two figures where they have the same shape and different sizes. So, for example, you might see two triangles. So they're both the same shape, they're both the right triangle, they have different sizes, but more importantly, their corresponding angles. Okay, corresponding angles are congruent, or in other words, the same size. Okay, that's one important thing. Their corresponding angles are congruent. When I say corresponding angles, I'm talking about, for example, a pair of corresponding angles in these two triangles would be the bottom left angle. Okay, these two are corresponding because both of these angles are in the same place on these two different figures. They're both in the bottom left corner. Another pair of corresponding angles on these two figures would be the bottom right corner. Okay, they both have a bottom right corner, so these angles here are corresponding. So again, corresponding simply means the same piece in the same place but on two different figures. So we have two different triangles and we're talking about the same piece, the bottom left angle, and the bottom left angle is in the bottom left on both of them. So the same piece is in the same place. Okay? So then of course there's a third corresponding angle, which would be this top angle here. And they both have that top angle. So the corresponding angles in similar figures are the same size. Okay, they're congruent. So if this is a 90-degree angle here, this is also a 90-degree angle here. It wouldn't make sense for all of the smaller triangles angles to get smaller, because if you recall correctly, triangles, all triangles, no matter what shape or size, all three, they have a total sum of 180 degrees for their three angles. Every single triangle, if you add up their three angles, will get you 180 degrees. So the degrees of the angles inside a triangle don't vary based on the size of the triangle. All triangles have 180 degrees inside them. So first things first, their corresponding angles are congruent. That's number one about similar figures. So same shape, different sizes, and their corresponding angles are congruent. Or in other words, the corresponding angles are the same size. The second thing that you need to know, and this is probably one of the most important things about similar figures, is that their corresponding sides are proportional. And if you remember back from chapter 6, when we talk about proportional, that means that we have two equal ratios. So what I mean when I say that the corresponding sides are proportional, what that means is if, for example, I decide that I'm going to do little side over big side as my ratio. Okay, I'm going to do a little to big ratio. And I take a look, we'll do a very simple one to start with. Okay, if I do little to big with my corresponding sides, so again, corresponding is the same piece in the same place on two different figures. So the left side of both of these triangles is corresponding. So little one would be 3, big one is 6. Okay. We'll do the bottom side next. These bottom sides are corresponding because they're both the bottom side of the two triangles. Okay, little one first, big one second. Then we'll do the hypotenuse. Little one first, big one second. What you're going to notice when I say that their corresponding sides are proportional, remember proportion means two equal ratios. Well, the little to big ratio here, if you look, all three of the fractions or ratios created by their sides reduce to 1/2. Okay. So one thing you could say, for example, is you could say that these similar figures have a scale factor of 1 to 2. For every 1 inch on this triangle, I have 2 inches on that triangle. Okay. Or they have a proportion of 1/2. So one of the triangle sides are half the size of the other one. Now, it's not always going to be quite so obvious what the proportion is or what the scale factor is here with the triangles. I mean, you could very easily have two triangles that have a scale factor of 7/13, which is going to be much harder for you to just look at the triangles and go, oh, they have a 7/13 ratio or proportion here going on. So that's why it's very important, if you are going to try to figure out if two triangles are similar, then you need to make sure you take the time to write out the corresponding sides in ratio form or fraction form, and then you need to take the time to reduce them and ask yourself, when I reduce all three pairs of sides, okay, do they all simplify to the same fraction? If this is true, and you get something like 1/2 equals 1/2 equals 1/2, then you have similar figures or similar triangles in this case. Now, more than just triangles can be similar. You can have similar squares or similar pentagons or similar octagons, whatever it may be. But we use triangles because there are fewer sides to have to compare, and so it's the simplest place to start when introducing the concept of similar figures, because there's not as much time involved in figuring them out and solving them and whatnot. So we're going to do one more example where I'm going to put some numbers up on these triangles, and we're going to try to figure out if in fact they are similar. And then after that, we're going to talk about what can we do with this information? How can we use this information to find missing pieces of similar figures? And we'll talk a little bit about that here in a minute. But first, I'm going to change the numbers and do another example. So if you're given two triangles, and each triangle has their sides labeled, so we might do 6 and 15. We will do 10 and 25 here, and we will do 7 and 16 here. So what we would do if we want to figure out, are these two triangles similar? Again, we're going to take their corresponding sides and set them up as ratios or fractions. So I'm going to do, again, little over big. You could do big over little, but you have to be consistent. Okay? If you're going to do big over little, when you write out your fractions, all three of them need to be in big or little format. If you're going to do it as little over big, all three of them have to be in little over big format. So I'm going to do little over big again. So we're going to do the left sides first. So we have a 6/15. Then we're going to do the hypotenuse. We have a 10/25. And then we're going to do the bottom sides, and we have a 7/16. So at this point, if I want to know, are these similar triangles or similar figures, I would reduce all three of my fractions and see, do I end up getting the same ratio or fraction or proportion in the end? When you reduce all these, you also could call what you get in the end. If they all become the same fraction or ratio, you can call that your scale factor. Like before, I had a 1 to 2 scale factor. But we're going to reduce 6/15 first. 3 goes into both of these, so I'm going to reduce this to a 2/5 ratio. 5 goes into both of these, so this will also reduce to a 2/5 ratio. However, 7/16 actually is already simplified, so I do not have similar figures. Even though 2 of my sides are proportional, the third one is not, so I do not have similar figures. So this one right here is causing me to not have similar triangles. So that's how you test to see, do I in fact have similar figures. Now, if you do have similar figures, like let's say I changed this and we had an 8 and 20, so now I have a 2 to 5 scale factor, or the proportion here is 2 to 5. For every 2 inches on this side, I've got 5 inches over here. Same thing for the bottom, same thing for the hypotenuse. If I take 8/20ths and I reduce it, just like the other two before, I'm going to get 2/5 because I reduce it by 4. 4 goes in the 8 twice and goes in the 25 times. So now I do have similar triangles, and what I'm going to do, and this is going to be something that you're going to be asked to do on your practice sheets and on the word problem sheets and whatnot, I am going to take one of those sides away. Now we know this x is supposed to be 20 because I had all this information up here before, but what we're going to do now is we're going to pretend for a moment like we didn't know this was 20, and we're going to say, okay, now I have a missing piece of this triangle. What do I do? Well, if it states in the problem that these two triangles are similar, then what you're going to do is you're going to set up your corresponding sides in their ratio or fraction form. So 6/15, 10/25, and 8/x. And what I do at this, what you want to do at this point is, because these are similar, all three of these fractions are supposed to be equal. They're supposed to be, because they're proportional, right? We said before that in order to be similar figures, your corresponding sides are proportional. Proportional means you have 2 equal ratios or more. 2 or more equal ratios. We have 3 equal ratios now because my corresponding sides are supposed to be proportional, or in other words, they're supposed to be equal ratios. So these 3 fractions we know are equal. Okay? So at this point, I want to know what x is. If you remember correctly, back in chapter 6, we talked heavily about how when you have 2 equal fractions or ratios, you can cross multiply and then solve for x, because when I do 10 times x and 8 times 25, I'm supposed to get the same answer on both sides. So for example, if I take 2/3, which is equal to 4/6, 4 times 3 is 12, which is equal to 2 times 6, which is 12. So if I do 8 times 25 and get 200, it should be equal to 10 times x, which is 10x. I now have a one-step equation. Since I want to get rid of the 10 that's being multiplied, I would divide both sides by 10, and x would equal 20, because 200 divided by 10 is 20, which is what we had there before anyways. Now, I did not have to do the cross multiplication of 10/25 with 8/x. I could have also chosen the 6/15. But the one thing I didn't have a choice about is I had to use the 8/x because it contains the missing side. It contains the x. But at this point, 8/x is equal to both of these fractions. So I could have put 6/15 here as well, cross multiplied, and I would have gotten the same answer in the end. Now, one thing I suggest you do, you can very easily do what I just did and cross multiply with the 10/25 or cross multiply with the 6/15. However, the bigger these numbers are, the more complicated that one-step equation is going to be, and the more complicated the cross multiplying is going to be, and the more time-consuming it's going to be. If you can reduce, if these ratios are not already fully reduce one of them, so I could reduce my 6/15 to the 2/5. Okay, 6/15, remember, if we reduce it, that means 6/15 is equal to 2/5, and 10/25 is equal to 2/5. Okay, which means 8x is also equal to it. So now I have much smaller numbers to work with. Before I had 8 times 25 and 10 times x, so my numbers were much bigger. Now I have 8 times 5, which is 40, and I know that's equal to 2 times x, which is 2x. Now I have a much simpler one-step equation to solve that will still get me the answer of x equals 20. So I suggest you, for your steps, if you want like a list of steps you're going to first, you want to set up your ratio, your corresponding ratios. Okay? You're going to set up those corresponding ratios. So the little over big, so the 6 over 15, the 10 over 25, and the 8 over x. 2, you're going to reduce the ratios without variables. And then third and final step, you're going to cross multiply the ratio that has your variable in it with the reduced version of your other ratio. So I had the 6 over 15ths, I reduced it to 2 over 5, so then I cross multiplied the 2 over 5 with the 8 over x. Okay, because the 8 over x had my variable in it. There's no point in cross multiplying two fractions if you don't have a variable in one of them, because the variable represents what we're looking for. It's the missing piece. Now, you will also find that sometimes you'll have more than one side missing. With similar triangles, you can actually have up to 2 sides missing, and you can still find out what both sides are equal to. So I'm going to do a quick example of that. So I'm going to replace that 10 with an n, and I'm going to show you this real quick. Again, you're going to follow the same steps. First step, set up your ratios. I have a 6 over 15, I have an n over 25, and I have an 8 over x. Okay? Now we know all three of these are equal because these two triangles have been, it's been said to us these two triangles are similar. So that means their corresponding sides are proportional, which means they set up, when you set them up in ratio form, they should be equal to each other. Okay? So all three of these ratios I just set up are equal to each other. Now, in this fraction, this fraction here, or this ratio here, contains my x. This ratio here contains my n. This one, I have a 6 and a 15. I have no variable there. So I'm going to reduce this fraction, which will reduce to 2 over 5. At this point, if I want to solve for both sides, I can only solve for one at a time. This is basically two problems in one. So I would set my n over 25 equal to the 2/5, solve the one-step equation, and I'd have n. After that, I would set my 2/5 equal to the 8 over x, cross multiply, and then I would perform the one-step equation, and I would find x. So it's just two problems in one. So that's all there is to similar figures. If the next video will actually be on chapter 10, section 1.